We've talked about using sample data to make inferences, that is, to estimate or make predictions about the population. In this video, we're going to go and discuss that estimation in greater detail. And the process of estimation includes the following steps. Number one, we want to define the population carefully. Number two, define the relevant population parameter, for example, the average annual salaries of a hospital's clinical staff. Number three, we want to select the sampling method. For example, we might want to use simple random sampling. And then number four, we collect the sample data. So we collect a sample or a subset of the population of the hospital's clinical staff. And then we apply an appropriate estimator or a formula to that sample statistic or to the sample data to calculate the sample statistic to estimate the population parameter in which we're interested. What we've done so far is to calculate point estimates. We calculated the mean, a specific 1-point estimate of the population. And as a reminder, a point estimate is a single value. In other words, it's a single point derived from a sample, and it's used to estimate a population variable. So we took the entire population, and we're trying to estimate that sample that value, whether it's a mu, the population mean, or let's say it's the standard deviation. We're trying to estimate that, and we take a sample, and that sample mean that we get is a single estimate. That's our best guess of what the population mean is, but it's only a single value. Now what we're going to do is use that point estimate to help determine a confidence interval. But first, what is a confidence interval? A confidence interval estimate is a range of values constructed from sample data so that population parameter is likely to occur within that range at a specified probability. The specified probability is called the level of confidence. So a confidence interval is the point estimate plus and minus the margin of error. With a point estimate, what we're saying is, I don't know what the value of the population parameter is, but the value of the sample statistic is my best guess. That single point value is my best guess. When we use interval estimation, we're saying, I don't know the exact value of the population parameter, but I'm 95% confident that the value falls between the following two numbers. Now, we'll talk about this a little bit later, and that statement's not exactly accurate, and statisticians would fault me for saying it that way, but just keep that in mind for now, and we'll expand on that a little bit later. The margin of error is the maximum expected difference or error between the sample mean and the true population mean that's dependent on the level of confidence that we've chosen. So think about the confidence interval like this. You're taking the point estimate and you're adding the margin of error to one side, the positive side, and you're subtracting that margin of error from the point estimate, and now you have a span or a range of data, or range of values, within which you expect that the population parameter will fall, or the population value. So if we're talking about mean, we would expect that the population mean would fall within point A and point B, for example. We'll look at two similar situations to compute a confidence interval, one when we know the population standard deviation and one we don't. But first, we'll talk about the factors that are affecting the confidence interval estimates. The width of a confidence interval is determined by these three things. So we use the sample size and the standard deviation in the calculation to determine the range of the estimate, of the confidence interval estimate, that is. And then the desired level of confidence is that one value that we use our research expertise to choose. And if we don't have a lot of research expertise, we can use what's traditionally used, or we do some searching in the literature in our field to determine what is the level of confidence that's usually selected or traditionally selected in our discipline. We'll start out by looking at the formula for estimating a confidence interval for a mean when we know the population standard deviation, which frequently we don't know. So again, the confidence interval is a point estimate, in this case the mean, sample mean, plus and minus some margin of error. So this whole calculation here, the z times the standard deviation divided by the square root of n, that is our margin of error. The formula is the point estimate, x bar plus and minus the z-score times the standard error, sigma over the square root of n. Okay, so we have the formula there, and we're going to plug in values to that. But the important thing to remember here is that the mean is the point estimate, and then we add and subtract our margin of error, and that's how we create our confidence interval. As I stated on the previous slide, we, the researchers, choose the level of confidence, and that's what determines the z-value. Traditionally, people often use 95% and 99%. How can we tell the standard error is affected by the standard deviation and the number of observations in the sample? Well, because one is the numerator and the other is part of the denominator. So let's take a look at this formula just a little bit closer. And again, the important point I want you to take away from here is that a confidence interval is built off of a point estimate plus and minus a margin of error, some margin of error. There's going to be a formula that we stick in there, and that develops the margin of error. For now, we're using this formula for the margin of error. So here are the pieces of the confidence interval. You have the confidence interval is equal to, in this case, it's a point estimate, which is the mean, plus and minus the margin of error. Now the mean is broken down into a z-score and the standard error. The standard error is the standard deviation divided by the square root of this number of n, the sample size. In other words, the standard error of the mean. So what we have here in the circle is this is our standard error, and then our z-score multiplied by our standard error creates the margin of error, which is the red rectangle. And again, we use our choice of our comfortable level of confidence to determine the z-value used in the margin of error calculation. Go ahead and read the margin of error definition on the screen. Pause the video if you need to. Now earlier I said that the way that I described the confidence interval explanation wasn't exactly accurate. Well, what it amounts to is that if we took every possible combination of a sample size x and built a confidence interval from that, remember every possible combination of sample size x, like we talked about when we did the central limit theorem, and we built built a confidence interval off of it, we would find, if we did a 95% confidence interval, that about or 95% of the confidence intervals that we created would capture the population parameter. So the population parameter here is mu for the population mean, but 5% would not. In other words, for those 5% of the time that we create, or the 5% of the confidence intervals that we created, essentially were wrong. We didn't capture the population mean. We said it was between here. We believe that it's between here, and in this case it's here, so we're wrong. But again, that's if we calculated a confidence interval for every possible sample of sample size x. And the way it's worded up here, for a 95% confidence interval, about 95% of the similarly constructed intervals will contain the parameter being estimated. Also, 95% of the sample means for a specified sample size will lie within 1.96 standard deviations of the hypothesized population. So assume that we don't know the population mean. If we selected a lot, maybe several hundred samples of X observation and built confidence intervals around them, we would expect about 95% of the confidence intervals we create out of our samples to include the actual population mean. And I say about 95% because I said if we select a lot, maybe several hundred samples of X observations. Now if we took every possible combination of samples of X number and we created confidence intervals off of them, then we could say that 95% of the confidence intervals we created would capture the population mean, 5% would not. Let's go ahead and do an example. In this case, we do not know the population mean. We know the sample mean is 45,420. Hence, our best estimate of the unknown population value is the corresponding sample statistic. The sample mean is of $45,420 is a point estimate of the unknown population mean. That's our single best guess of what we think the population mean is based off of the sample that we took. The reasonable range of the values is the confidence interval that we're going to find. So we have our scenario here. American Management Association wants to have information on the mean income of middle managers in the retail industry. Random sample of 256 managers reveals a sample mean of 45,420. The standard deviation of the population is 2,050. The association would like answers to the following questions and decides to use a 95% level of confidence. So here are our questions. What does the population mean? What is a reasonable range of values for the population mean? And what do these results mean? Now this formula, that's the same formula we had in pages before. The important thing to remember is that a confidence interval is, regardless of what we're looking for, this just happens to be the mean, but the confidence interval is a point estimate, that's your single best guess, plus and minus some margin of error formula. In this case, this is the formula we're using for the population mean, trying to capture the population. And it's made of the z-score times the standard error, which the z-score times the standard error is the margin of error. If you go back a couple of slides, you'll see that. Think about what parts of the formula we can fill out right now. And I kind of gave you a little bit of help by underlining pieces of the scenario there. The only thing we don't know is what? Take a look. It's our z-score. And why don't we know that? Because we're the ones that are going to determine that based off of the 95% level of confidence that we're given. Normally, we would determine which level of confidence we're going to select based on our expertise. And if you're looking at the 4th edition of the Andy Field book, you can look at page 890. The table on page 887 accounts for only, that starts on page 887 accounts for only one tail, the left part of the distribution, or the left distribution. The 95% confidence interval refers to the middle 95% of the observation. So the remaining 5% are equally divided between the two tails, the right distribution that we have up here. In our book, we use the 2.5% to determine the z-score because it's only indicating one part of our formula, so or distribution, so we have to take that as a 2.5% there. And our z comes out to 1.96. So now we have the last piece of information that we're missing. Finish filling in the blanks, and we have our 45,420, which is our best guess of a single value of the sample mean, in other words, our point estimate, plus and minus our margin of error, which is our z-score, times our standard error, which is our standard deviation divided by the square root of n, equals 45,420 plus and minus 251. The confidence limits are 45,169 and 45,671. So with 95% confidence, we estimate that the population mean is between 45,169 and 45,671. The $251 that we came up with here is referred to as the margin of error. And what does all that mean? Well, if we were to select many samples of 256 managers and construct a 95% confidence interval for each sample, we could expect about 95% of those confidence intervals to contain the population mean. Now, if we selected every possible sample combination of 256 managers and constructed a 95% confidence interval, we could expect that all 95% of these confidence intervals, we could expect that exactly 95% of these confidence intervals would contain the population mean, 5% of them would not. Keep in mind that's just a way to theorize or to understand the concept of the confidence intervals. If we could select every possible combination sample of 256 managers, then we would have the population and we wouldn't have to create a confidence interval. We could take the population value and actually capture or calculate the population mean. So what is the interpretation of the confidence limits 45,169 and 45,671? Well, we stated it before, but again, it's with 95% confidence we estimate that the population mean is between 45,169 and 45,671. What do you suppose we should do if we don't know the population standard deviation? Well, we can use the sample standard deviation to estimate the population standard deviation, and instead of the z-distribution, we use the t-distribution. And here are the characteristics of the t-distribution. It is, like the z-distribution, a continuous distribution, and it's bell-shaped and symmetrical. The difference is there's not one t-distribution, but rather a family of t-distributions. They all have a mean of 0, but their standard deviations differ according to the sample size n. And the t-distribution is more spread out and flatter at the center than the standard normal distribution. But as the sample size increases, the t-distribution approaches the standard normal distribution. There's some debate, but most statisticians agree that as you approach a sample size of 30, the t-distribution is very closely aligned with the z-distribution. So the t-distribution is flatter, and think about that for a second. What's that going to do to our confidence interval? It's going to increase our confidence interval because the t-distribution spread out more. The confidence interval formula is very similar for using the z-distribution and the t-distributions. Remember, the confidence interval formula is a point estimate plus and minus a margin of error. It's just a matter of how we calculate those things. So in the z-distribution, it's x bar, which are point estimate, plus and minus our margin of error, which is the z-score, times our standard error. In the t-distribution, it's the same thing. We have a point estimate right here, plus and minus a margin of error. Now the margin of error here is determined by a t-score times the standard error. Again, only this standard error is determined by the sample standard deviation divided by the square root of n. And guess what? Of course, we have an example for a confidence interval using the t-distribution. And what is it that we do not know that causes us to use the t-distribution for the confidence interval? Well, you can see it right on the screen. The population standard deviation. And remember I said about statisticians generally agreeing on a sample size of 30, the t-distribution roughly equates the z-distribution. So when you have a sample size that's greater than 30, you can go ahead and use the z-score. In this case, our scenario is that a tire manufacturer wishes to investigate the tread life of its tires. A sample of 10 tires driven 50,000 miles revealed the sample mean of 0.32 inch of tread remaining with a standard deviation of 0.09 inches. Construct a 95% confidence interval for the population mean. And we want to know is it reasonable for the manufacturer to conclude that after 50,000 miles the population mean amount of tread remaining is 0.30 inches. So I've already highlighted and actually broken out the important parts of the scenario, or the parts that are going to become our calculation here. And note that the symbol alpha in here is used to indicate the confidence level. This is a little bit confusing here. Don't get too hung up on it, but this is all this is telling you is how you determine your t-score. And to find our value, you would turn to page 893, Appendix A2 of your Andy Field Discovering Statistics Using SPSS, 4th edition. You'd move across to the level of confidence desired, which is 95%, or in other words, 0.05 here. we choose the row with the appropriate number of degrees of freedom, which is our n minus 1, or 10 minus 1 is equal to 9. And then we find under the 0.05 column our value of 2.26. So our t value is 2.26. Do you remember what the z value was for the same confidence value? If you remember, it was 1.96. So if you go back to our calculation here, remember it's point estimate plus and minus a margin of error. So if our t value here is bigger than our z value was, then you can see how it would make the confidence interval larger. So if we go back to our formula, we have our point estimate of 0.32 plus and minus 2.26 times 0.09 divided by square root of 10. In other words, we have our point estimate plus or minus our margin of error, or excuse me, plus and minus our margin of error, and we get our lower limit of 0.256 and our upper limit of 0.384, and we can conclude that the manufacturer can be reasonably sure that the mean remaining tread depth is between 0.256 and 0.384 inches. So another way to say it is that with 95% confidence, we believe that the population mean remaining tread depth is between 0.256 and 0.384 inches. I'm going to walk through another example here of using SPSS to calculate your confidence interval, and we'll use this with screenshots. Look for another video where we actually go in and calculate it within SPSS. That's forthcoming video. So the scenario here is the manager of the Inlet Square Mall near Fort Myers, Florida wants to estimate the mean amount spent per shopping visit by customers. A sample of 20 customers reveals the following amounts spent, and I'm not going to read all those off to you here. First, we'll use the formula, and here's the formula that we used before, only we punched in the appropriate values, and we find that the endpoints of the confidence interval are $45.13 and $53.57. Again, we have our point estimate of $49.35 plus and minus our margin of error, which we just calculate out by finding our t-score, and then we multiply that by our standard error. We get a 4.22, which we add to our point estimate, and we subtract from our point estimate, so we get a value over here on this side and a value over here on this side. Those values are $45.13 and $53.57. So we could say with 95% confidence we believe that the population mean would be between $45.13 and $53.57. And as a further to help further understand, we could say that it's reasonable that the population mean could be $50 based on this confidence interval, but the value of $60 isn't in the confidence interval, so we would conclude that the population mean is unlikely to be $60. Is it possible? Yes, because we don't have all of the population data. We've made an estimate or an inference. Let's look at how we would do this in SPSS and Megastat within Excel. So in SPSS, we would go to Analyze, Compare Means, One Sample T-Test. We would take our variable and put it in as the test variable. We'd go and click on our options, and we would put in our confidence interval percentage of 95%. We'd hit continue, we'd hit OK over here, and then we would run the analysis, and we would get this output here. So you can see in SPSS we have the same mean. It's just out to 4 digits of precision compared to 2 digits of precision here. And then we have our standard deviation of 9.01211, our standard error of the mean 2.01517. And now you'll notice if we go into here, we have 9.01 as our standard deviation, and we have 9.01 plus a few more digits of precision here. The important thing to note here, though, is the mean value here, which is our point estimate, and here are our lower and upper limits that we'll get in our output from SPSS. And again, if you're going to do this in SPSS, it's Analyze, Compare Means, and One Sample T-Test. If you're going to use the data analysis tool pack in Excel, you would go to Data, Data Analysis, and Descriptive Statistics. For Megastat, you would calculate the mean, Megastat, confidence intervals, sample size, confidence interval, and click on the mean value. So let's take a look at selecting an appropriate sample size, because we want to know if we're taking the right size sample. And there are three factors that we're looking at to determine the size of the sample. And if you remember in our formula, the sample size is important in both of our formulas in calculating the confidence interval. So it's important that we try to select an appropriate sized sample. And when we do so, none of the factors, the three factors that determine the size of the sample, have any direct relationship to the size of the population. So the point is, we don't need to know the population to select the appropriate size of the sample. We use the level of the confidence desired, that's what we choose, the margin of error that we are willing to tolerate, which is really based on the level of confidence that we're determining, and then the variation in the population being studied, which is the standard deviation. And what if we don't know the population standard deviation? There are a few things you can do. You can conduct a pilot study. If you have a large enough access to a large enough sample size, you can collect a small sample, do a study on the small sample of the population, determine the sample standard deviation, and use it as an estimate of sigma, the population standard deviation. You can use a comparable study. So if somebody else has done a similar study before, you can use their standard deviation as an estimate of population standard deviation. You can use a range-based approach. And to do the range-based approach, you have to have the largest and smallest values in the population, or an estimate of those values. And you have to know that the empirical rule applies, that nearly all, or 99% of about 99.7% of the observations fall within plus and minus 3 standard deviations, a total of 6 standard deviations. In other words, the distance between the largest and smallest values is 6 standard deviations, or about 6 standard deviations. Again, that's only about 99.7% of the observations. Remember, there are 0.3 that are not included in that, but it's close enough. We can estimate that 1 standard deviation has 1/6 of the range of the observations, since the distance between the largest and smallest values is 6 standard deviations. And we talked about ensuring we have the appropriate sample size. And how do we get that sample size? We convert the margin of error formula to solve for n. So our margin of error formula, if you remember on the prior pages, when we had our confidence interval formula, we had the margin of error was z times the standard deviation divided by the square root of n. Well, algebraically, we can rearrange this formula so that we're solving for n, and we get this calculation right here. Z times the standard deviation divided by the error, or the margin of error as it's likely called, and we square that. On this page we have an example for sample size determination. In this one we're using Megastat, and Megastat provides a nice easy method of calculating the sample size. We're not going to go in and do the example. I just want to leave this here as a reference page for you and an example that has the answer for you so you can compare your work. And to get to the sample size in Megastat, to calculate the mean, you go to Megastat, confidence intervals / sample size, and then the mean. And that's all for this video. I hope it was of help to you, and if you need to, go ahead and review it. Watch it again. Have a great day. Thank you.